Hello, and welcome to Introduction to Linear Algebra with Wolfram U. My name is Devendra Kapadia, and I'm the manager of Calculus and Algebra at Wolfram. But I also enjoy teaching mathematics, and in fact, I have taught mathematics at high school and college level for many years. It is a great pleasure to share my ideas about linear algebra with you in this course. This is the first lesson of the course, so let's begin by asking the question, what is linear algebra? Well, linear algebra means different things to different people. So for some people, linear algebra means linear systems. So here is a linear system of equations. You have the equations x plus y equal to 5 and x minus y equal to 1. And that, of course, is just a pair of straight lines in the plane, which you can see graphed over here. Now, given such a system, we have some key questions to ask. So, for example, does the system have a solution or not? Now, in this simple case, of course, we have that x is 3 and y is 2, and that's the solution. But in some other cases, you may not really have a solution at all, or it might be quite hard to find a solution. So we have a notion of an approximate solution. So either you have an exact solution or you have an approximate solution. But in any case, for some people, their definition of linear algebra is the linear algebra is the study of linear systems of equations. But other people have a more geometrical view of a subject, and they'll say that, oh, linear algebra is the study of geometric transformations. So for example, here in this figure, you have a reflection about the line y equal to x in the plane. And this, of course, is a linear transformation because the image of a line is again a line. And given such a transformation, you could ask, find an algebraic description of this transformation. Or you could ask, are there any lines that are left unchanged by the transformation? So for example, over here you can see that the line y equal to x is kind of invariant or unchanged for this transformation. So some people would tell you that linear algebra is the study of linear geometrical transformations. But of course, there is a third viewpoint which is quite popular these days, and that's the notion of matrices and determinants. So a matrix is just a rectangular array of numbers in rows and columns. So here's a matrix. It's got two rows. First row is 5, 4, second row is 6, 7, and two columns. So that's a 2 by 2 matrix. And system of linear equations and transformations can actually be represented using matrices. Now, a matrix is a collection of numbers. That's a huge collection typically, but with every matrix, you have its determinant. So the determinant is just a number that's associated with the matrix. So for example, in this case, you have the determinant is 11. That comes out by doing 5 times 7 is 35, 6 times 4 is 24, subtract them, you get 11. And this determinant, although it's just a number, it contains important information about the system of equations or the transformation that you're studying. So in the modern world, a nice way to think about linear algebra is that it's a study of matrices and their determinants. And of course, that's useful because in this day of computers, we can store matrices quite easily with powerful computers. And so doing linear algebra is actually a very fruitful way of solving problems in the modern world. Now, of course, there's a long history behind this subject, but let me just give you a brief history of the subject of linear algebra as it relates to this course. So, of course, the Chinese and other civilizations knew about linear algebra, but to me, the course has history going back to roughly 1750 when Gabriel Cramer published a study of determinants. And in fact, he published a rule for solving systems of equations. And a little later, in 1800, the famous German mathematician Carl Gauss actually talked about elimination to solve equations and the least squares method, which we'll talk about later in the course. Now, Gauss was a genius, but his real interest in this case was to try and do geodesy and apply these ideas to real world problems. But the mathematical theory of linear algebra really began around 1850 when James Sylvester used the term matrix or womb for an array of numbers. And Sylvester and his friend Arthur Cayley worked on matrices, and Arthur Cayley actually published his work on the theory of matrices around 1855. So Sylvester and Cayley were great friends. In fact, in those days, it was hard to make a living doing mathematics. So Sylvester was an actuary. He worked in insurance. Cayley was a lawyer, and they talked about law in the day and talked about mathematics in the evening. But together, they set up a lot of what we call linear algebra today. And a little later, in 1888, Giuseppe Peano actually talked about vector spaces. So in the modern mathematical world, vector spaces, of course, were very, very important. But in this course, we'll not worry too much about them. We'll mostly work with matrices and determinants as taught to us by Cayley and Sylvester. Okay, so the question is, what happens today? Well, today, people all over the world use linear algebra in different ways. So in different professions, there are their own uses for linear algebra. So for example, if you do mathematics, you might want to study the geometry of a surface, and then you'd use linear algebra to actually make a system of coordinates in which you can do your matrix manipulations. Engineers use linear equations to study the motion of fluids, to design airplanes and such things. Data scientists will have their own linear models to make predictions about data. And in fact, data science is a big driver for linear algebra these days. Now, if you study physics, then physicists will use linear algebra to study quantum mechanics, the study of atoms, and in fact, these days, they also use linear algebra to build quantum computers. And finally, it's not just the sciences, but the economists have always used linear algebra for doing things like input-output matrices. And in fact, a lot of modern linear algebra came around because of these applications. So not only have the applications been big users of linear algebra, but they actually have driven the modern development of the subject. So linear algebra is very much an applicable subject in the modern world. Now, of course, you might ask the question, why should I study linear algebra? Well, I'll give you a few reasons for studying linear algebra. So first of all, it has very broad applications in the real world. We just saw that. If you apply for certain kinds of STEM degrees, it's an essential course which you'll need to cover at some point. And in fact, in some cases, they may even ask you, how good is your linear algebra for advanced degrees? Now, even if all that were not true, I would say that learning linear algebra is a great thing because linear algebra is a major intellectual endeavor, and to study it is a major intellectual achievement. So I would say that to study linear algebra is to master one of the most important branches of modern mathematics, and I strongly urge you to do it with this course. Okay, so now let me tell you a little bit about the course itself. So the main goal of this course is to give you a thorough introduction to linear algebra. And to do that, I'll begin by talking about linear equations and linear transformations. And then we'll talk about matrices and their determinants. And then we'll move on to more advanced topics like eigenvalues and other things. Now, to make sure you understand what's going on, we will have exercise and quizzes going on to accompany the lessons. And as far as proofs are concerned, there will be no formal proofs in the course, and we'll focus on understanding the subject without any proofs. Now, my main goal in all this is to show you that linear algebra is really easy. And I hope that when you're done, you will feel that you've learned linear algebra in a very useful way, and you'll be ready to apply it in your own work, whatever subject it is that interests you. Okay, so the question is, who is this course for? Well, you might be an ambitious middle schooler or high schooler who wants to learn advanced mathematics, become an engineer, become a data scientist, whatever. And then I would say to you that to study linear algebra is a great way to to start learning modern mathematics. So this course is really designed for people who are learning linear algebra for the first time. Or you might be a busy professional who needs to get some knowledge of linear algebra to, let's say, take a course on machine learning or whatever, and then this course should be a nice refresher for you. But really, I think that this course is good for anyone who wants to know how the Wolfram language can be used to learn and do linear algebra. So if you love mathematics and you love programming, then this course is certainly for you, whether you're a student, a professional, a teacher, or anyone else. So I think this course is meant for a wide variety of people, and I've tried to keep it as simple as possible. Okay, so that brings me to the end of this introduction. And to summarize, linear algebra is the study of linear equations and geometric transformations. But the modern approach to the subject will use matrices, determinants, and of course, at a more advanced level, it will also use vector spaces. Now, to know linear algebra is important because it's an essential tool for students in many fields. So that's the broad introduction to the course, and in the next lesson we'll begin the course formally with an introduction to linear systems. So thank you very much. I hope you have enjoyed this introduction. I do hope you'll pursue this course with great sincerity and wish you good luck. Thank you.